Network Virtualization Software Defined Network. I am Dr. Rajiv Mishra, Professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. Content of this lecture. This lecture we will cover the architecture of software defined networking and its application to the networking in the cloud and edge computing. We will also cover network virtualization in a multi-tenant data centers, and we will see the case studies of VL2 and NVP. Need of software defined network. The traditional networking has the problems that software defined networking is addressing, such as the complexity of the existing networks. In the sense, the networks are complex just like the computer systems, having systems with the software, but worse than that, the networks are primarily the distributed systems, and even more worse that there is no clear programming APIs and only the knobs and dials to control certain functions are made available. Therefore, the complexity of the entire network embedded into its devices, which is running hardware and software together at multiple places of the deployment, and it is running like a distributed systems. As I told, it is the embedded systems, that is the devices are having the software also, and this will be running like the distributed algorithms without much control, and therefore it is a very complex networks which are existing in present today. Now, second important thing of is the network equipments are traditionally proprietary, that is the network equipments are having the integrated solutions, or you can say that they are embedded devices running operating system, softwares, configuration, protocol implementation, hardware, often comes from different or major vendors. So, the complexity of existing network and network equipment which are traditionally proprietary from major vendors will result into that it is very hard and time sensitive to innovate new kind of networks and new services or modify the traditional networks more efficiently. Let us take the consideration of the traditional network. So, in traditional network, configuring a router, for example, router is running the BGP routing protocol. So, to do this you are given only a configuration files, and using that you can configure the router. Now, hundreds and thousands and tens and thousands of such network devices, routers, switch, firewalls are existing throughout the network. These devices, and once it reaches these devices, then these configurations have to be interpreted by the software running on those routers and the implementation of those protocols that runs in a distributed algorithm and arrive at the routing solutions that produce the ultimate user behavior that is installed in the network hardware. So, here the policy is embedded into the mechanism. So, it means that the network routing to achieve low latency or high utilization, that is the intent of the network, that is nothing but the controls of the networks are also embedded into the distributed protocol and that are in standardized implementation. So, in this example you can see in the traditional networks, these particular devices often have the configuration files. These configuration files at every devices need to be now pushed, and you know that if let us say hundreds and tens and thousands of devices are running into a network, in a traditional network, so configuration file for all the devices is quite tedious. Why? And another thing is that the configuration, now once it is modified in the configuration file, now it has to be effective by the software which are running on those particular devices. They are nothing but the router softwares, and also the implementation of that particular protocol will take these new configurations which are specified in the configuration files and are trying to effective in the distributed routing. So when the new routing solutions or protocols are required as the packets or as the traffic arrives in the system, so that particular aspects of the network which is desired from the ultimate behavior now will be effective than in that using the configuration file. So what the configuration file is? The policies. So policies are now embedded into the individual devices. It's not, and for example, if you want the entire network, now network routing will be now effective to achieve the low latency and high utilization of the network, then these controls which are already embedded into these particular devices and required in the distributed algorithms, which are nothing but in the standardized implementation, has to do a very little means implementation perspective. Therefore, software defined networks are preferred over the traditional networks. So software defined networks, what it does is the traditional softwares and the operating systems are built on the layers and APIs. Now it begins close to the hardware with build the low level interfaces that gives direct access to what the network switching hardware is now doing. So therefore, what is being done in the software defined network is the controller, which is also called a logical centralized controller, which communicates with these distributed devices and switches in the network. Now this particular aspects will have two parts. So first is that all the control part is collected together and is called logically centralized controller, which then communicates with all the devices with respect to the control of that particular devices or control information. So the goal of this logically centralized controller is to express the intent or a goal at one location and keep the widely distributed switching gear as simple as possible. So that particular aspect, you know, that data plane, and this data plane API will receive the instructions of the control instructions from a centralized place called logically centralized controller. Therefore, the programming of the control of the entire network is kept centralized with the help of logically centralized control in software defined network, whereas the forwarding or a data plane remains there with the devices. So put the intelligence, if you put the intelligence in a logically centralized location, on the top of that you have to build the software abstractions that helps us to build the different applications or network operating systems if you want. So the key ideas of software defined network is a division of policy versus mechanisms. If you recall in the previous slide, when you say policy, that means logically centralized controller, its responsibilities is about the policy that allows us to build the software abstractions on top of it using those policies. The second component which divides with the policy or separated out with the policy is called the data plane. So, there are low level interface and the programmatic interfaces are available for this particular data plane to be integrated with logically centralized controller using APIs. So, let us consider as an example called NOC system as a software defined network controller, SDN controller. Now, to identify the user's traffic, a particular user or the computer to send the traffic through the network, and that traffic through the network is going to be tagged with an identifier, that is VLAN, with a which identifies that particular user. So, to instruct the network about finding out this identity of the user traffic or specific, we match the specific set of the relevant packets and look at the location where this traffic comes in from, as well as the MAC address to locate, to identify the identity of that user's traffic. So, we are going to construct an action that should happen in this case, tagging, adding that VLAN tag to the traffic. Now, then we are going to install that action onto the specified set of packets in a particular switch. So, we are basically telling the switch that if you see this type of traffic, then you have to do that. In addition, commonly the SDN controller have some kind of topology discovery, the ability to control the traffic and monitor the behavior of this particular traffic. On the right side, you can see from the NOCs that on the user authentication statically set up the VLAN tagging rules at the user's first hop switch. Now, here you can see that user to VLAN function, which is now defined as VLAN ID. Now, here for packets from the user, now you have to add a VLAN tag, so that you can do this particular monitoring with this SDN controller. Now, let us see about the ideas, what ideas this SDN will bring into this type of change in the traditional networks. So, a programmatic low level interface with the data plane, as I told you, is available, so that the mechanisms and the policies are being separated. So, data plane will implement the mechanism as far as the policy is considered. It is centralized control based policies. So, higher level abstractions will make these kind of control much easier. So, let us trace back the evolution of software defined network and also how it has brought into a flexible data planes. So, evolution of software defined network is driving towards making the networks flexible as of today. Now, starting with 1997, the label switching or MPLS, now it matches the labels and executing the actions based on those labels, adding a very primitive level of flexibility into the traditional networks, and that lay down any path that we want in the network for certain class of traffic. That was a very rudimentary or primitive type of flexibility into the network with the help of MPLS. Now, you have to go beyond the simple shortest path forwarding, good optimization of the network of traffic flow to get high throughput for the traffic engineering, setting up the private connections between the enterprises and the distributed systems are yet to be evolved. So, next in that sequence of development, in 2005, routing control platform was given by Caesar during NSDI 2005. Their centralized computing to the BGP routes, they are pushed to the border routers via IBGP. So, here in this particular figure you can see network control protocol. Now, what it does is it does the centralized computing to the BGP routes, and then it will push it to the IBGP routers. Similarly, in 2005, about the logically centralized control, there was another solution called 4D architecture. A clean slate 4D approach to the network control and management was given by Greensburg 2005. It says that logically centralized decision plane separated from the data plane that you can see. So, decision, that is the policy, is separated out from the mechanism or the data plane. That is the logically evolving the concept of today's software defined network. Ethane in 2007, that was given by Casado in the conference called SIGCOMM. It also gives you the centralized control which enforces the enterprise network Ethernet forwarding policy using existing hardware. Finally, in 2008, the open flow came into an effect, and this standardized interface to the data plane was given, and general purpose programmability at control was there. Now, software defined network gives you the different opportunities such as open data plane interface, where hardware and software was clearly defined. Hardware, that is with the standardized API, is easier for the operator to change the hardware for the vendors to enter into the market. It is not now specific the major vendors, it's any vendor can provide the solution using this software defined network, and it gives an opportunities here in this case for open data plane interface. Software concerned can more directly access the device behavior. Now, centralized controllers are concerned, direct programmatic control of the network is now possible using centralized controller. Software abstractions of the controller solves the distributed problem only once, then just write the algorithm. Libraries, languages to help the programmer write network applications, systems to write high level policies instead of programming. Now, performance and scalability are some of the challenges of software defined network. So, controlling the network through devices to respond quickly with latency concern, that is the capacity concerns. Now, distributed systems challenges still they are present, that is the network is fundamentally your distributed system. Resilience of logically centralized controller brings into the challenges for software defined network. Imperfect knowledge of the network state also becomes a challenge in the software defined network. Consistency issues between the controllers are also taken as the challenges. Regarding the architectural challenges of software defined networks, now protocol to program the data plane. Now, there are various type of protocols exist, such as OpenFlow to use OpenFlow to program the data plane, or to use NFV function, or to use white box switches. There are many other such possibilities exist. So, this becomes an architectural challenges of implementation of software defined network. Now, devices the right control abstraction, that is using the programming OpenFlow, that is for too low level device in the terms of devising the right control abstraction, but what are the right level abstraction to cover the important uses becomes architectural challenges. Now, coming to the multi-tenant data centers in the edge, which is more prevalent, that is edge data centers. The challenges now are similar to the cloud. Let us understand that multi-tenant data center challenges. So, cloud is shared among multiple parties as well as the edge, and gives the economies of the scale based on how effectively it is able to share. Now, to share the cloud among the multiple tenants, there is a bit more work to do. So, the key needs for building the multi-tenant cloud or edge data center are agility, location independent addressing, performance, uniformity, security, and network semantics. Let us understand these 5 very important aspects to bring our data centers, that is edge data center or a cloud data center, to a multi-tenant data center. So, the first aspect is called agility. That is, agility means that use any server for any service at any time. Now, whether it be it a edge data center or a cloud data center, agility has to be implemented, and agility means any server for any service at any time. So, this means agility means that better economy of the scale through increased utilization. That means pack compute as best as we can for high utilization. If we ever have a constraint, then it is going to be a lot harder to make the full use of the resources. The second important thing is improved reliability. If there is a planned outage or an unexpected outage, move the services to keep running uninterrupted the applications or the services. Now, service or the tenant can mean a customer renting the space in a public cloud application or service in a private cloud as an internal customer. So, the traditional data centers, you can think of the racks containing those hundreds and thousands of servers, which are now having the network together with the top of the rack switch, which is having another level of aggregation switch to network the racks, and these aggregation switch again will have this network together using the routers. So, you can see it is a 3-tier architecture which is being effective in a traditional data center. Now, this traditional data centers is having the challenge that is called lack of agility. So, let us understand using this particular figure why there is a lack of agility in the traditional data centers. So, here the tenants in the silos means one rack or a part of the cluster is devoted to a particular service, which is shown here in different colors. Now, this results into the poor utilization, inability to expand, and therefore, it is a lack of agility. Now, another lack of agility is that IP. Why it is happening? Because IP addresses are locked to the topological locations over here. So, you cannot directly move, for example, 10.0.6.0 and then having the subnet of 24. This particular entire service which is running in this particular rack cannot be moved to some other part of this particular rack, because they are having an IP address locked to this particular topological location. So, this brings into the lack of agility in the traditional data centers. So, the key needs to bring the agility is that since agility is location independent addressing, normally the racks are assigned the different IP subnets, because subnets are used as the topological locators, so that we can do the routing. Now, to move some of the services out there, we are going to have to change its IP addresses, and it is very hard to change the IP addresses of a live running services. Now, second important thing is tenants IP addresses can be taken anywhere. So, tenants IP addresses to be taken anywhere and independent of the location, the data center, without notifying the tenants that its location has changed. So, large over subscription ratio, that is 100% or greater if there is a lot of communication between both the sides, will be about 100 times now lower throughput than communicating within the rack. So, these are some of the key needs to be used in implementing the agility. Second key needs is the performance uniformity. About other than agility, the other important aspect here is called performance uniformity. Means that wherever the virtual machines are, they will see the same performance and latency. So, if the virtual machine is running in this portion of the rack or in this portion of the rack or some other portion of the rack, so they will see the same performance and the latency. Now, smaller units of the compute that we have divided our services into and put them anywhere in the data center and maybe on that same physical machines. So, the performance uniformity is again the key needs. Third important key needs is about the security, that is untrusting the applications and the user sitting right next to each other and can be inbound attacks. So, to protect our tenants in a data center from each other in both public data centers as well as in a private cloud, you do not want them to have to trust each other. So, therefore, the aspects of security is also quite important, such as microsegmentation, that is separation of different regions of the network, much finer grained divisions and control of how the data can flow, isolate or just control just data flow between the pairs of application or the tenants that should actually be allowed. And fourth important thing is about the network semantics, that is to match the functional service of the traditional data centers. So, not just layer 3 routing services, but also layer 2 services, discovery services, multicast, broadcast, etc. have to be supported. This aspect is called network semantics. Now, let us understand with this use case that is called network virtualization in a multi-tenant data centers. Case study is VL2. So, VL2 is a scalable and flexible data center network which was published in ACM SIGCOMM 2009. So, network virtualization case study of VL2. Now, here we will see how all 5 key needs are implemented, that is agility, location independent, addressing, performance, uniformity, security and network semantics. This is very much important for networking of the data center services. Now, let us understand this case study of VL2. Now, VL2 started with motivating environmental characteristics such as Greenberg in its paper. So, he has given this graph that is about the traffic. So, increasing internal traffic is a bottleneck, means that the traffic volume between the servers is 4 times larger than the external traffic. Now, rapidly changing the traffic statistics, that is to take the traffic matrix in 100 seconds buckets and classify them into 40 categories of similar clusters of traffic matrix and see which of the clusters appear in the measurements. So, over time rapidly changing and no pattern to what the particular traffic matrix is. So, design result is that it should be non-blocking, that is all the network which is a 3-tier network which was shown in the previous figures. So, that requires the non-blocking fabric, that is how high throughput for any traffic matrix that respects the server NIC rates, the fabric joining together all the servers, we do not want them to be the bottleneck. So, the failure characteristics is again the motivating environmental characteristics. So, analyzing the 300,000 alarm tickets, 36 million error events in the cluster. So, 0.4% of the failures were resolved in over 1 day, 0.3% of failures were eliminated all the redundancy in the device group. So, the design result is that it requires a class topology, that is a particular kind of non-blocking topology which are scale out instead of scale up. So, VL2 taking this experience, VL2 has given its physical topology which is explained over here. So, the traditional data centers will have this kind of the layer 2 networking, autonomous systems, and here you have the switches and here top of the rack switch. Together they are aggregation switch, top of the rack switch. This particular layer 2 is now connected with the routers, and then it will be a core routers. So, they are called data center layer 2 and layer 3 networks are there. So, AR you can understand there is access routers, and AS is aggregate switch, and S is the L2 switch, TOR means top of the rack switch, and CR means the core switch. So, core switch is now connected to the internet. Your data center will be now connected to the internet for offering the services, or maybe inter data center networking is also done through the network, where two core routers will connect with each other. So that was a traditional network. Now let us take this entire network and using VL2, it will be converted into this particular form. So here you can see that the top of the rack switch will remain as it is, but it is having the flexible pool of servers owning AAs, that is the aggregation points. Then this aggregation switches here, you know that so aggregation switch AS, here you can see that now will be now given over here with a different aggregation switch connecting to the top of the rack switch TOR, and over that now you will be having kind of layer 3 networking devices. So here there are now intermediate switches which will run the link state network carrying only the LAs. So here this is an example, it's a cross network between the aggregation and the intermediate switches. So these are the intermediate switches and the aggregation switch, which provides a richly connected backbone well suited to VLB, that is the network built with two separate address families, topologically significant locator addresses, LAs they are called here, locator addresses, and the application addresses. So these addresses are divided in two parts. One is called AA, that is called application addresses, and the other is called locator addresses. So you can see that now they are not tied up, this entire topology is not tied up with the IP, but rather it is now divided into the locator addresses and the application addresses, and this particular division is implemented in top of the rack switch, in the aggregation switch and the intermediate switch. So aggregation switch and intermediate switch, they are being virtualized, and therefore it brings into the concept the locator addresses and the application addresses to make it independent with the IP. So the routing in VL2, if you can see that for an unpredictable traffic means it is difficult to adopt. So this leads us to a design that is what is called oblivious routing. It means that the path along which we send a particular flow does not depend on the current traffic matrix. So it uses the variant load balancing. So for the routing on hypercubes, takes an arbitrary traffic matrix and make it look like a completely uniform even the traffic matrix. So take flows and spreading evenly over all the available paths, spread the traffic as much as possible and route the traffic independent of the current traffic matrix is called variant load balancing. So the routing implementation here, you can see that this was shown in the previous slide, that is the link state routing, which is carrying only the locator addresses and the application addresses. So it spreads the arbitrary traffic pattern, so the uniform among the top layer switches that are called intermediate switch here in this case. So here you can see that it will be divided, spread across these intermediate switches. Now to do that, what VL2 does is assigns those intermediate switches and any cast address, the same any cast address for all the switches, and then at top of the rack switch can send to a random one by just using a single address, and if we push the ECMP, we will use a random one of those paths that are the shortest one, that you can see over here that particular traffic is now pushed up and is being evenly distributed across these intermediate switches. Now, as all of the paths are shortest because of all intermediate switches are the same distance from the top of the racks. So, ECMP is going to give the full breadth of possible paths to any one of those switches just by naming the single anycast address of all of the intermediates. So, ECMP lets us select from one of those paths, then one will be picked from any particular flow and we send it to that intermediate switch. Now, that outer anycast is wrapping an inner header that actually has the destination address in this design. We will forward it from there to the destination. Now, any service anytime is done here in this way. You can see the physical layer, physical network layer is different set of IP addresses now called the locator addresses tied to the topology used to route, and layer 3 routing is effective using that called OSPF. Now, indirection or virtualization layer means a directory server that maps the application level addresses to their current locators. So, VL2 has the agent that runs on the server that will query the directory server and find the application address to the locator address mapping, and then when it sends the packet to the, and then it wraps the application address into an outer locator address that we have explained. So, application and tenant layer, the application or tenant of the data center is going to see what is called the application addresses. These are the location independent, same address no matter where the virtual machine goes, and they are going to see the illusion of the single big layer 2 switch connecting all of the applications virtual machines. So, any service anywhere. So, end-to-end example if you see. So, here the application sends to the address, to the application address, which is 20.0.0.56. Now, this particular host will encapsulates with the help of a directory service. So, what it does is, now it will take this application address 20.0.0.56 and then it will query to the directory service where is this application address. Now, it will respond for the locator address 10.0.06 by referring this particular directory service. So, from this application address it will now resolve into the locator address, and for locator address what it does is now send it via this top of the rack switch to this locator addresses. So, locator address will now, this locator address will now decapsulates, and finally, now this particular locator address 10.0.6, now this intermediate switch will now forward it to 10.0.06 top of the rack switch, and here this particular this locator address in turn will resolve it for this 20.0.0.56, and this will be nothing but the application address of the destination in this case. So, the message is, so the application which is 20.0.0.55 can send it to that application address called 20.0.0.56, and that resolution end-to-end example we have seen here in this particular figure. So, did we achieve this agility? This is the question which we have to see. So, the location independent addressing, that is application addresses are now location independent, it is not dependent on IP address. Now, second important thing is L2 network semantics, that is the agent now interprets and handles L2 broadcast multicast. Both of the above requires layer 2.5, that is shim agent running on the host, but the concept transfers to the hypervisor based virtual switch. Now, performance uniformity is also implemented, that is a cross network is non-blocking and non-oversubscribed here can be implemented uniform capacity everywhere, and ECMP provides good load balancing, but the performance isolation among the tenants depends on TCP backing off to the rate that the destination can receive, leaves open possibility of fast load balancing. Next important aspect is called security. So, directory system can allow or deny the connections by choosing whether to resolve an application address to a locator address, but the segmentation not explicitly enforced at the host. Now, where is the SDN in this entire discussion? So, let us take this example of a directory servers. They are nothing but the logically centralized control, orchestrate the application location and control communication policies. The host agents, that is dynamic programming of the data paths. Now, we are going to see the next solution, that is called network virtualization, cases using NVP. So, network virtualization in a multi-tenant data center. So, we are studying this network virtualization case study using NVP. This paper was published in 2014. So, NVP approach to the virtualization, to the network virtualization platform was introduced here, network virtualization in multi-tenant data centers in 2014, and this comes out to a product developed by Nikira startup that was acquired by VMware later. So, let us understand here the arbitrary network topology. So, here you have the physical network, any layer standard 3 network, and you have a network hypervisor. It will replicate the arbitrary topology, and any standard layer 3 network and network hypervisor and network tenant want to build. So, virtual network service, if you can see over here, the model as the sequence of data paths element that represents those switches, and these data paths elements, each one of them is nothing but an open flow forwarding table. This means that table will match on a certain signature of a packet header and take certain resulting actions like dropping the packet, modifying certain fields in the packet, forwarding, and so on. So, the idea is that we can model the switching and routing gear with the right sequence of the right open flow tables that we set up. So, here you can see this is the access control link table, and which is shown over here in this case of virtual network service. So, there is a packet abstraction where virtual machines are able to inject the traffic into the virtual network, and there is a control abstraction where the tenants are able to define this entire virtual network pipeline, that sequence of open flow tables. So, that is the interface that the tenant is given, at least the lower level interface that the tenant is given to able to program the virtual network. So, virtual network, that is the tenant control abstraction, is shown over here. That is nothing but the network hypervisor controllers are now controlling all those open vSwitch that you can see is nothing but running on different servers, and which is nothing but the physical L3 network. So, challenge of the performance is that large amount of states to compute. So, full network state at every host with the tenant virtual machines, order of n square tunnels for the tenants with n virtual machines. So, solution is to automated incremental state computation using n-log declarative language. A logical controller will compute the single set of universal flows for a tenant, translated more logically by physical controllers. So, therefore, pipeline processing in the virtual switch can be slow. The solution is the first packet of the flow through the full pipeline, thereafter put an exact match packet entry in the kernel. So, tunneling interfaces with TCP segmentation offload, that is called TSO. So, here NICs can't see TCP outer header because of the virtualization. STT channels adds fake outer TCP header. So, conclusion, in this lecture we covered the need of software defined networks. We presented the key ideas and challenges in software defined networking. So, we have also covered the challenges for multi-tenant data center networking, that is called agility, location independent addressing, performance uniformity, security and network semantics, all 5 aspects in a multi-tenant data center networking, which is very important in building up the edge and cloud data centers. Then we covered the network virtualization in a multi-tenant data center with the case study of VL2 and NVP. Thank you.